Okay, today what I'd like to do is I'd like to go through the four problems that were given in the second test. This first problem is a gas turbine engine with a diffuser and a nozzle. In this particular problem, I did ask you to use the IG model, the ideal gas model. In this particular problem, one does not need to use the gas dynamics test app, but rather just the the gas power plant problem. What we have is we have what's given in the problem is that the velocity coming in is the velocity of the aircraft itself, which is 360. It's coming in at state 1 with static conditions of 28 kPa and minus 32 Celsius. What happens in the diffuser is that all of the kinetic energy is converted into pressure and temperature. So state 2 has 0 velocity, and we assume that the diffuser is isentropic. And so the pressure and the temperature that then are established would be the stagnation conditions. The static and the stagnation conditions be one and the same. And so that's going to give us the state going into the compressor, the temperature and the pressure associated with that incoming state at 2. We're going to go through the compressor, which is 11-to-1 pressure rise. The compressor is we are going to assume that it's isentropic. That's going to then get us up to a pressure as well as a temperature associated with state 3. The combustion chamber is going to be assumed to be constant pressure, and the input of fuel is going to then provide a temperature at the outlet of 1250 Kelvin, and so that's going to define state 4. State 4 then expands through the turbine to state 5. Now, what we have in this particular case is that we know that the turbine is isentropic in nature, and the other thing that we know in this particular problem is that the work generated by the turbine is the work that was required by the compressor. And so that's going to allow us then to determine what state 5 is. Once we have state 5, and state 5 will again be 0 velocity, as was states 4 and 3 and 2. And once we get to that state 5, we're then going to go through the nozzle. The nozzle will be isentropic, and the condition at the outlet of the nozzle will be the pressure of 28 kPa. That was the pressure at that particular altitude. And so with that pressure being known at state 6, we will then be able to determine the condition at the exit of the nozzle, and that being the kinetic energy or the velocity at state 6. Once we obtain the velocity at state 6, we'll then be able to determine the change in the flow momentum, which is just the m dot times the change in the velocity between state 6 and state 1. State 1 is at 360. That's going to give us the thrust, and then when we multiply that thrust times the aircraft speed, which is the 360, that is going to give us the power. And so we'll go ahead then with those assumptions and those conditions, and we'll go into the test software. So again, the application is the gas, the gas power cycle. And so I select this. It is going to be an ideal gas, air, that is treated as an ideal gas and not a perfect gas, but an ideal gas. And we want to do that because the temperatures will be a little bit higher, and so there will be changes in the properties of C sub P, and C sub V is a function of temperature. And so we then select the application, and we're ready then to move on with our various cases. And so what we know in this particular problem is it's air. The incoming pressure is 28 kPa, and the incoming temperature, as shown, is minus 32 Celsius. Minus 32 Celsius. Okay, we also, in the problem, we are told that the m dot through the system is at 35 kilograms per second. And so basically, this is our incoming condition, except for the fact that our velocity is the velocity of the incoming air, which is the motion of the aircraft engine at that particular altitude. So we've got the static conditions at the altitude, we have the velocity, and we know the m dot. And so everything then is determined in this particular case. Now we're ready to isentropically slow this down to see what happens to the pressure and the temperature as we go through that isentropic process. And so state 2 is going to have the same entropy as state 1. It's going to be the same m dot throughout, m dot 1. And as we said, we're bringing it down isentropically. Now, in order to actually get this final condition, I'm going to go ahead to the device panel, and I'm going to say for the first device, which is going from state 1 to state 2, there is no work being generated and there's no heat transfer. And so with this particular device determined, then the state panel is then it allows us then to calculate what are the conditions at state 2. So had this been the gas dynamic application, the pressure and the temperature here would have corresponded to the stagnation temperature and pressure. But in this case, all of the kinetic energy has turned into pressure and temperature ready to go into the compressor. So we have state 2 defined. We're now ready to go into to figure out state 3. State 3 is once again an isentropic compression, and the compression is compressing the fluid by a factor of 11. So it's 11 times pressure 2, isentropic. So the entropy is the same and the m dot is the same. And so now we have the state of the fluid prior to going into the combustion chamber at state 3. We see that the temperature is about 600 Kelvin. And now at the pressure, this pressure here is the pressure going into the combustion chamber, which will be the pressure coming out. We're going to assume the combustion chamber is constant pressure as we've done throughout. And so we have then state 3. We're ready to go to state 4. Now state 4 again is at the same pressure as state 3. We are told in the problem that the temperature prior to the turbine is 1250 Kelvin. Again, that's in the problem. And we also know the m dot. And so the m dot is m dot 1. So now we know the conditions coming out of the combustion chamber. Now, while we're at it, we'll go ahead and we'll set up device 2, which is the compressor. And the compressor goes from state 2 to state 3. And it was done in an isentropic fashion with no heat transfer. And so this then will allow us to determine from 2 to 3, this should allow us to determine what the work is of that compressor. Now, it's not giving us the work. Let's see what happened here. So, again, it's state 2. I'm sorry. It should. Okay, I'm going to recalculate state 2. Something didn't happen there. Okay, let me go back to my device panel. Go back to here. Okay, that should have calculated like we saw before. State 1, state 2, and that's our state 1. This is our state 2. Okay, now state 2 is determined. State 3 is determined. State 4 is determined. Our device panel then, there's our device. This is then, okay, so this now is the work of the compressor. We see that it is, in terms of megawatts, it's a minus 10.5. And so that's the work that's required to cause the 11-to-1 pressure rise, as we saw, and that is then the power that's going to come back from the turbine. Okay, if I go into the next device, which is device 3, that is the combustion chamber. So the combustion chamber is state 3 to state 4. No work is being done, and we see that this is then the work of the heat that has to come into the combustion chamber. Okay, so now we're ready to go to state 5. State 5 is the exit of the turbine. And what we know is at state 5, this amount of work was actually generated. And so we are going to use this particular term here in our device panel to give us then the conditions at 5. So I'm going to come back to the state panel. I'm going to select state 5. We don't know what the pressure is. We don't know what the temperature is, but we do know that it's isentropic. And so we're going to say that the entropy is the entropy coming in. The m dot is the m dot throughout the system. Again, we don't have these two conditions here, but now we can go and we can set up device panel, and that device panel is the device panel from 4 to 5. Okay, that's going through the turbine. We know that there's no heat transfer, but then the work that's going to go in here is going to be equal to the negative of the work dot EX2. And so since we calculated the compressor, the work for the compressor, and it was negative, okay, the system knows that it's a negative number, and what we have to do is then put in that the work actually being generated by the turbine is this amount, the negative of that amount. With that piece of information, we should go back to the state panel and find that it now calculates the state 5. So a little bit different than what we've had before, but again, having done all the different device panels and having that assumption that just enough work is generated by the turbine that the compressor needs, that then gives us state 5. So state 5, we see the pressure went down to this, the temperature went down to this, still zero velocity and still has the same m dot. Now, another way to have generated state 5 is, since the work is just the change in the flow energy, this is the J term, we could have put in that this J at 5 is actually, if I went back to 4, it's J4 plus the J associated with the difference between 3 and 2. So we could have put that work in as a function of the flow energy. But it's probably easier to put it in through the device panel, because indeed we recognize that the device panel is calculating for that particular device. The device panel is just calculating the m dot J difference, and so we could actually put J5 in as a function of J4, knowing that it rises by a certain amount. Okay, so now we're ready to go to our final state, and our final state is state 6. And what state 6 is the nozzle, and what the nozzle is doing is, again, isentropically, it's going to allow the fluid to expand to the pressure of the surroundings. And so it's going to expand to 28 kPa. It's from 276. And it's going to do it isentropically, and we're also going to go into the device panel and say that there's no heat transfer and no work. Same amount of flow here. And so what happens there is we'll see that the pressure and the temperature will go down and the velocity will increase. And that's what we're after, is that increase in velocity due to the re-exchanging of the flow energy. So here we then, our state 6 is simply equal to the pressure at 1. That's the 28 kPa. isentropically from 5, which is the exit of the turbine, same m dot 1, we're going to turn off the velocity 6 here, because that's what we want it to calculate. And now once we go into the device panel and we say that there's no work or heat transfer generated in this isentropic flow, this expansion from 5 to 6, we'll come back and it will then give us what the velocity is. And that's the kinetic energy term. Because in that nozzle, the J stays the same. And the J just goes from enthalpy and kinetic energy rearranging. And so here's our state 6. We go to our final device panel. Our final device panel is going from 5 to 6. And again, no heat transfer and no work. Calculate. Go back to the state panel and calculate. And let's see what happened here. Got the pressure, the temperature, entropy. Let me do a super calculate. And now we go back to our state panel, and now state 6 has been calculated. So what we find is, again, this flow energy at the exit is the same flow energy as what we saw here, 378 or 738. So the flow energy has stayed the same, but what has happened is that flow energy is the enthalpy plus the kinetic energy term. And so when we turned off the zero velocity, we do get a kinetic energy that adds with the lowering value of the enthalpy at that temperature. So now we have everything that we need then to calculate the numbers. And so if I go to the super calculate then, we see in the cycle panel that for the flow rate and interest, this is the heat transfer that came in through the combustor. And we know that that corresponds to then the m dot of the fluid, the m dot of the mass flow through, and then the fuel m dot is going to then be determined. So we need to put this amount of heat transfer in by allowing a certain kilograms per second of fuel to be burnt. Okay, so we will calculate that number, and then the other numbers that we need to calculate are the thrust and the propulsive power. So we we come into here, and the value of interest that we need to have is the heat transfer associated with the combustion chamber, and we saw that that was this device here, this from 3 to 4, and so it was Q dot 3. Okay, so it's an input of Q dot 3. So we come back here, and just to make sure that we have that Q dot 3, we see that that is the value in kilowatts. Now, if I then say that the fuel rate is just going to be equal to that Q dot 3 divided by the 41,500. The 41,500 was given in the problem as how many kilojoules per kilogram of fuel. And so by taking the kilojoules per second and dividing it by the kilojoules per kilogram, this will then give us the fuel flow rate. So this tells us that we need to bring in 0.616 kilograms per second of the fuel to provide that heat transfer to the 35 kilograms per second of air going through the system. So that answers the question about the rate of fuel consumption. We also know in this particular problem we were asked for the velocity at the exhaust gases, and that was just velocity 6. And velocity 6 is, let's see, velocity 6, return, and could not be evaluated. Okay. Let me supercalculate here again. Let me go back to device panel here. Let's recalculate this. Okay, so velocity 6 is there. I'm going to go back to the I/O panel and then put in equals velocity 6. And we see that it's 990.11. And so now we're ready to calculate the thrust. And the thrust of the engine, as defined, is just really the the difference in the momentum. And so we have m dot 1, which is the flow rate. That is the mass flow rate of air. And that m dot 1 now is just times the difference in the two velocities. And so velocity 6 minus velocity 1. Velocity 1 was the original velocity of the air coming in. Velocity 6 is the 990 that we just determined. And so the m dot v is momentum, and we take the difference between the outlet and the inlet, and that then gives us the thrust from the momentum equation. And so our thrust then is calculated to be 22,000 kilonewtons. Okay, and so the power then is just equal to that thrust value times the velocity of the aircraft. Okay, force through a distance per time. And so there's a force of 22,000 kilonewtons, and the distance per time is the 360 meters per second. And so when I then do that calculation, we then see that the power developed is this value right there. So again, the thrust now that thrust, let's think about the units. Okay, so m dot is in kilograms per second. Velocity is in meters per second. And so this really here is in newtons. And so when we take this newtons times times meters per second again, we then have power in watts. Okay, so again, the units are going to be watts because it's actually joules per second. And so this term right here in power, if I move the decimal place 3, and then if I move the decimal place 6, then I would have 7.9 megawatts of propulsive power. And that then answers all of the questions that were then asked for in this particular problem.